Hi, Professor Densmore. Today we're going to be talking about our image recognition model that we made. This one is just, we're going to start at the baseline. We're going to skip 2, we're going to go to 3, and then we can go to 4, and then we're going to go to 5. If you want to skip 4, there isn't much of a difference between 1, 2, and 3. It's kind of just showing the limits of creating a recognition model for 10 categories from scratch. It's quite difficult. So here we're just loading in a bunch of packages. We're on Jupyter Notebook just because it's a lot better in terms of doing this kind of stuff because it is in Python. These are just some images that we have saved in our local directory. There's a link to it on Kaggle, and it's basically just 10 different categories of animals. So this is just importing the images for the training set and the validation set. This is just getting the noun and names. And then this is just a data augmentation function. So basically we're just flipping it, rotating it, and zooming it randomly as the model is training on these images to kind of keep it on its toes and make it dynamic so that even if it sees a flipped image, it should be able to identify the right category. So this is our model. It's a very shallow neural net. We have one output layer and kind of just one hidden layer inside. Very little parameters, 368 parameters, so this will go by really fast. And you can see as we run through our epochs, which is just how many times it's training itself on different 20% images of like a certain set, it'll pick a different 20% badge every single time. And you can see it's quite fast, around 40 seconds. And you can see this model overfits significantly. So the highest we got validation accuracy is 39%, which is a little bit better than on naive. So naive would just be randomly guessing a certain category and you would get it 10% right. So it's a little bit better, but not very good. You can see it overfits significantly to our training set, and then performs extremely poorly in our validation set. And the performance kind of deteriorates after the epochs because it gets overfit that much. And you can see our performance here, not very good. What we desire is that this validation accuracy is kind of lined up with training accuracy in a smooth kind of way, and that this is, in terms of the training and validation loss, that this gap is closed and they're at least pointing into the same direction. So that's what we're kind of aiming for in terms of our goals. Imported images at a new size, so higher pixel density, which should help. We also did another data augmentation. I believe these are still the same parameters. But here we added kernel constraints and intermediate dropouts. And basically what intermediate dropout does is that instead of dropping out when going to the output, it actually drops out during the when the nodes are communicating in the hidden layers. And this kind of, again, just keeps it on its toes, keeps it so it's not relying on certain paths in order to identify an image, trying to keep the overfitting a little bit lower this time. And we add kernel constraints, which basically does the same thing, and it's just basically not allowing each node to communicate freely with all the other nodes, and it's kind of getting rid of some noise features but we can't really control if it's getting rid of good communication between the neurons, so good features versus bad features, but hopefully this helps, and we're doing it every single layer, and we adjust hyperparameters. This is kind of random. We had to play around with this, and this took quite a bit of time just because you can see the compiling takes a long time. So here you can see, because we added kernel constraints and dropouts, the total params that we're actually training is half less than Model 3. And you can see we ran 30 epochs this time. But we actually broke the 60 mark, and we actually got up to 67. I believe that was our best performance. And you can see here that our training accuracy and our validation accuracy is quite close now. So there's a lot less overfitting, and even though the accuracy isn't 80%, we would like to get it to 70% at least, but we probably would have to train it for like 20 more epochs, which is just an obscene amount of time because it's 420 seconds per run. And I think a lot of the times it broke because my computer would like start sleeping and I would have to restart, which was quite frustrating. And that's probably one of our biggest challenges when doing this, is that when you're trying to play with the hyperparameters and you're running through these long epochs to see if it will perform better, especially when you're trying to squeeze out, just a little bit more accuracy, takes a lot of time and computing power. And that's probably one of the biggest things when it comes to machine learning is, the cost of computation is definitely a big factor. So you can see our accuracy has actually gone a little bit better. There's a little bit of jaggy because sometimes it does a little bit worse, sometimes it gets a little better. It's not consistent, but you can see at least it's going in the same direction now, and same for the loss function. So this was our best attempt in terms of training on the data set with a model that we make from scratch that we adjust the hyperparameters. So now we're going to go to MobileNet V2. So I don't know if you've heard of this, but basically it's Google's pre-trained neural network that's kind of optimized for identifying image categories. And what we do here is we're basically importing a new image size. We're applying the same data augmentation for it. We're initializing the model. And you can see there's many layers here, very, very deep. But what's surprising is that since Google has basically pre-trained their model, it's optimized so that it retains a lot of the useful features, useful communication between neurons that help with image recognition, and while discarding, some of the noise in there. So you can see that even though we have this many layers and these parameters are relatively high, we're actually only training on 2 million parameters. Right, so it's half of what Model 4 was. And you can see this has, we add a global pooling layer, which is kind of confusing. It helps, but we don't know exactly why. So yeah, here we input our images is 224 by 224. And here we have a summary of our model. So the MobileNet V2 was the one that you saw here, and then we add a little bit more layers over here, just kind of following like a guide of what would help our model the best. And you can see we only do 10 epochs here, but the runtime is significantly better. Right? So we're only running for 283 seconds per epoch. You can see our validation accuracy and training accuracy are very, very close. And we reached 95% accuracy at the end with 90% training accuracy, which is really, really good. Because there's virtually no overfitting and our model is relatively dynamic. You'll see this when we do a stress test on it. So you can see our performance here is very, very good. Like there's no very, very smooth. They all follow the same direction. So this model is obviously really, really good because it's an open source model made by Google after doing their kind of image recognition training on their supercomputers, trained millions of images. So the model is really optimized for doing this kind of work. So here we're just importing a lot of test images. These are just images that we got online off Google Images that kind of are a little bit different from the data set that we have. So we have dogs, spiders. In terms of butterfly, instead of using a real butterfly, we use the Butterfree from Pokemon to see just to kind of stress test it and see how it reacts and how dynamic it is and to little changes like that. We also have something called Fun, which I think is a unicorn. We have narwhals and humans, which none of them are in our categories. But we just want to see how the model behaves. So you can see here with dogs is really good. Got all of them right with really high confidence. With spiders, I got one wrong, but you can see that it's not exactly confident. So this is kind of how credit card fraud is detected. So if your bank detects a purchase that maybe isn't in line with normal behavior, it'll actually send you a text message because and it'll ask you, did you make this purchase, yes or no? And this is kind of what it's reacting around. Right? There's a percentage confidence that it outputs whenever you make a purchase, and if that confidence is really, really low, then to send the person a text message. So we can actually see this run. So I think it'll actually give us, I don't know if it gives us different, nope, just the same. Right. So with butterflies, it was actually pretty surprising that it actually knows that a Butterfree is actually a butterfly, which is interesting. This is a unicorn. So we actually ran this model before. It's just that my Wi-Fi went off. So this is like take 4. There was one time where I stopped recording, so I didn't record. So it thinks the unicorn's a sheep, which is pretty accurate in terms of the categories that we have. It's probably the closest to a unicorn in terms of shape and color. Narwhal, you can see it's not confident at all. Still calls it a sheep, but this you can basically discard, right? And then we have 4 human faces, which it sees as a cat with low degrees of confidence, sometimes in high degrees of confidence. I don't know why it is 76. So you can see even with the model performing so well on our training and validation set, when we give it an image that maybe isn't in line with the set that it was training on, like off Google Images, something more random with different colors and pixel density, it's a little bit shaky in terms of its performance. But that basically is our entire project. A lot of the layers that we have in here is explained in the PowerPoint, but just to go over some some new ones that we have that are different. So batch normalization, depth-wise conv 2D. So basically convex 2D, normal convex 2D, you're basically taking an image and you're trying to find features just in that kind of layer, right? That 2D layer. Whereas convex 2D splits that image into 3 different layers, with its own kind of feature attributes. And basically, if you can take an image and you can split it up into 3 different 2D feature layers, you have a better kind of understanding of what images have that kind of those same features, and that basically just helps it be more a little dynamic, on their toes, and it just learns more in terms of when it goes through an image. So yeah, thank you so much for listening, and have a great winter break.